FIU Bridge, guys. FIU Bridge. All right, what do I have here? This model in the background is to scale. I'm pretty close to the scale also on it. That's the number 11 and 12 upright would be here. That's number 11. That's the deck. That's number 10. The white bar, the white lines indicate post-tension bars. The thread, all thread, right there indicates a post-tension rod, rather. Not a bar. This did have a blister bar on top. The way they captured it, it's like a nodal area, a gusset of a design. And down here, it goes. This rod goes all the way through, and you see it right there, the nut. Not that good on that, huh? Let's see if I got lighting. Okay. So there's a nut inside there. Okay. So when I loosen this and I apply load on just the top only, no deflection in the deck, of course it will slide downwards. Of course it will slide downwards. But that's deflection of the canopy. Now, I made this model here. This is the post-tension bar model that I made up with all the rods in it, theoretically showing you that down the middle of the system there is no post-tension bars. So the only way to get from this bar, the post-tensioning cables from this side to this side is via rebar, reinforcement going, transversing the deck, which they did do. Now, this is a scale model, pretty close also, of the deck. And I'll turn this on the side. This was painted at one time. This is how I wanted to capture ideas that they came up with, capturing it from the bottom. And so I theoretically made up a design. And then I wanted to see what would happen if the deck was loaded in that span. Climbed on top, loaded it there, and not much came of that. I cut it to see if, then I filmed it to see if it would close. Nothing came of that. This is the diaphragm here, and a diaphragm on this end. As you can see, they're both the same size, untrue to the true diaphragms, which were smaller here, and significantly larger down the other end. The number 1 is the upright. This would be number 2 here. And as you can see, it's set back way far from the diaphragm, part of the diaphragm system. So it loaded differently than down here, whereas this loaded into the diaphragm. Now, I took liberty and I cut the number, just to see if it would close up. I cut the number 11 diagonal. And I loaded it here. We got a backhoe, and I crushed this downwards with the backhoe. And all I did was get this deflection here. As you can see what happened here. Loading it here at the canopy. And it did not translate to making this pass down to here. Now this is the number 12 upright. If I remove it totally, the system still works, which I showed in a scale model. Removing it totally, not connecting it, this system still works, taking the load. Now the diaphragm down here, and there's the A and B rod, and that would be those two rods there, A and B. Not sure which one's A and which one's B, but A went through. So B went through the upright here. Okay, A went through the deck. B, let's call B the upper one, went through it came out to the back of there and went through the upright. So the forces that they applied in it, some of it was in the diaphragm, and some of it was inside the this upright, this number 12. When they loosened so the engineering, all this was supposed to be pretty much, let me just say, I think it was pretty awesome. I give that to Denny Pate. I know we can slam them also, but I'll give it to Denny Pate that it was supposed to be an all-compressive system, not no tension and compression like a truss system might behave. It was all supposed to be all compressive, and that was accomplished through reinforcement, rebar, Concrete, of course, being rigid connecting forces. So we have the transportation over there. Once they loosen this up, the problem is in the staging area, they had cracks appearing across in the uprights. And this is all supposed to be compressive. So how can you get open cracks? Cracks would indicate it's in tension, going apart, and so it's no longer in compression. And yes, they were small cracks, but those cracks shouldn't have developed if you're under compression. It would be spalling, but not open cracks. And that's what was happening here. This had open cracks in multiple locations, including here. Now we talk about slide friction again. And the problem with that is that this can't slide. As you can see, when I load it there with the backhoe, this doesn't close up right here. It can't slide unless the deck deflects. The deck has to deflect, which means the post-tensioning has failed. It's elongating. It's becoming, hold on. Okay, my brain was lost there. It's relaxing. The post-tension cables are relaxing, and they can't support the system. Now, what takes over is the canopy and the deck. Now, when you look at this deck, sorry, this was painted and drawn onto and everything at one time. This is a pretty old model. There were some fractures upon this location here. So what happened was the deck, if you look at the diaphragm also, it rotated. So this didn't just fracture here. The canopy, with the post-tensioning bars not all being installed, because they came up short, there were like 4 up there instead of 6 of them at the time, this rotated. And I believe looking at it from this direction, it rotated clockwise. Looking at it from this direction, clockwise. And that, if you look at the back of the diaphragm, when you observe the cracks, you'll observe that, yeah, it's opening. It's the openings explain why one side is lower and one side is higher. When you look at the ruler they put down here, you can see it's almost inch or plus, if I recall, inch plus higher on the right side, the diaphragm side, than this deck side. And that means the diaphragm, when this fractured, rotated. And that happened after the post-tension rods were loosened. And when it loosened it, see, he thought this was a total compressive system, but the engineer that did his calculations, she was wrong on the post-tensioning holding this thing together. And that was indicated by those cracks, like I said. Now, when they also, the problem was when the sequence of post-tensioning structure was incorrect, I believe. If you look at the sequence, when they post-tensioned the structure in the staging area and it was all supported on the formwork, they initially post-tensioned number 11 and number 2. They were the last that should have been post-tensioned. But doing that, the deck had a different profile and stress in it, and then they post-tensioned the rest of the system. But the rest of the system was based already on this pre-stressed of number 11 and a post-test of number 11 and number 2. So when they removed the formwork from mostly besides underneath the diaphragm over the staging area, these cracks appeared. And right then they should have figured out that, oh, these should not appear. This is a compressor system. There should be no open fine line cracks, open cracks. The system is not staying in compression. So if it's not staying in compression, we therefore must be getting deflection in the span. They carried on. They went over there, they put it in place, took the victory lap. That day they released number 11 and number 2, and that was the A and B bars in each one. Remember, this diaphragm is much different than where it's set up further out from the diaphragm. This is a 4-foot, I believe, like 4-foot wide diaphragm down here on the base. This is approximately a 2-foot diaphragm down here, and the configuration of the bars wind up being differently as defaulted because of that design. So now, again, if we go back to the beginning, they post-tensioned number 11 and number 2 first. All right, that's just wrong. They should have did that last, since it was also going to be removed. It should have been, we don't need to worry about that. They assumed that this system by default, think logically. If you can remove the post-tensioning off of number 11 and number 2, that means the engineering assumed that this was automatically would be in compression. Therefore, you would get this slide friction thinking. All right? But the problem is it still can't slide because of the nodal areas are locked in. This is all locked in. This is what they call the blister bar up top. It's locked. It's locked to the deck. It's locked, locked, locked. Everything is locked. The deflection happened, let's see if I get this right about here, yeah, between 10 and 11. If you look at the video, slow it down enough, you'll see the deflection takes place here. When that haunches down, yeah, we get this is already, remember, we have pictures of this already fractured to hell. So it can't take compression either any longer because it's all fractured up. And yet they went back on there and put compression into it. And there was nothing to put, it was all fractured up. It was ridiculous to put compression into there. It's like me saying, well, let's put compression in here. We know it's just going to buckle if I try to put compression in here. This would just buckle. Same with this one. So, but that company, VSL, I believe it is, if I recall, they should have known that. They were expert repair technicians and professionals on repair of post-tensioning. And they should have known that this was not structurally sound to add that many kips to it. When they did that, what was the remainder of this connection was failed. They just blasted it apart. It destroyed it. So it now no longer had the nodal area, any remaining value here. And it transferred the span, the structural load path. This was removed because of the compression and destruction of it with post-tensioning. That put the load path from here up to here still as a rigid point, and then down across the deck into the diaphragm. This, if it could have done anything, would have been like that, like a little strut and tie, but the strut and tie is kind of weird. It would be like this. This is no longer capable. So it would be this, across the deck, and up here. Almost like a little, the shape like that, all right? But this wasn't able to hold because there only was one bar holding this on. Once they got into that one bar, they destroyed its ability to anchor and secure itself to the diaphragm. Remember, this stuck outside the diaphragm. It approximately made up that 4 foot, but it didn't work because this is 4 foot plus it doesn't go. It goes into the deck, not into the diaphragm, as I recall. All right, so now not into that 4 foot diaphragm down there. So when they post-tension they crippled this put it out of commission. This now had the system that's supposed to be in total compression now looking like this. Removing this as part of the system, you can see now that if I were to load this, it won't transfer down here. This has no value to it. It won't transfer down there, but it'll transfer to here. And now your span is from here to here, and the post-tensioning that was set up could not maintain rigidity in the deck. The deflection happened right about here because that's where it was most stiff, from here to here. All this was stiff down to there. This all worked. Where it was no longer the base of the deck, no longer be able to, the bottom plate, if you will, he considered this an I-beam, was no longer able to maintain its rigidity, deflecting here, trying to transferring the load here still. And I think he knew about it because in the meeting he said, we're going to try to capture, go back to the meeting, capture from the nodal 910 to the diaphragm. And that's why you see me do this, make up this little detail here. It did jack shit. It did not capture it. It did not transfer it back to the diaphragm. All right, so that's what it looks like. Again, I loaded that with a backhoe, and look at it. It stayed together. I'll stand on it. I guess I'll stand on it. And you see that, well, now it's going down because I did that, but the deflection is in the middle. You see, it didn't do anything. It's got a little bit, if we get deflection down there, we get a little bit of budding right here now, look. But what had to happen first? it had to have deflection in the base deck. So remember that. The base deck had to have deflection in it. That means the post-tensioning was in error. If you just take it by itself, like I said, and you just had the canopy being able to load downwards, it would slide this. But doing that, it would destroy the blister bar and also this nodal connection here. At minimum that, and also it would crank that area there, which would be here. And it would crank, then it would crank onto that one. You know, you would see multiple other flags. I saw no 910 intersection error problems with that would indicate that this held up pretty damn great. Again, going back to the engineer that did the post tensioning for him, she had it in the yard, and when the yard cracks came up, they said, we'll figure it out later why the cracks are. We don't know why they did it, right? That's the whole thing. We'll figure it out later. I don't know. But that's what he's saying. You know, I don't know. We'll figure it out. But the problem is that was showing it was no longer a compression system. Remember, his system was compression. Now let's talk about redundancy. Well, it turns out he did have redundancy in the bars. It did act like a truss system for some significant amount of time until he removed the post-tensioning bars, the number 11 and number 2. And again, her sequencing of post-tensioning was a major issue here. She also had post-tensioning of different kips in these two. All right, the ones closer to the diaphragm, the center of the canopy support, these had lower kips in value in the post-tensioning than the others. All right, so it was weaker in the middle now. Don't know why she made it weaker in the middle. All right, don't know why she did that, especially because this is where the center of the structure had direct loading into the base plate, the bottom plate, if you will. And remember, so that was D1. So D1 and D1 on this side, D2. Well, D1, D2. Okay, so I forget what that is on this side, but it's the opposing. D1, I forget what it was called over there. I don't have it written there. That D1 was less kips than D2, and yet it's closer in line to where this loading is off the from the canopy. And the canopy's not for free with that loading. All right. So this is literally post-tensioning cable, and you can see the strands. Let's get to the other end there. You can see the strands, the bundle. It's 7 of them. So 3 and 6 and 1 in the middle. When you clamp on this and you pull, not all of them elongate the same, all right? Because of the way it's set up. The one in the middle is straight. The rest are spiral. And the one in the middle doesn't elongate the same as the outer spiral. So that's also an issue when you're with your relaxation and when you're dealing with post-tensioning. So this is a long nose post-tensioning device. It's pretty damn heavy, no reason for me to pick it up right now, but that's a long nose. Alright, so there's your post-tensioning, and it pulls, so it's got you put clamps on the end of the strands of the cable, and you pull it and you elongate it, and then the wedge locks it in. There's the rest of the device for it there that powers that. It's a there you go. That's the rest of the device that powers that. Well, that's interesting. That was a wind pressure difference. So I want you to reimagine. I'm just teasing about the reimagine. I want you to rethink this. I've gone through the models many times. Every last strand, everything that was available, images, the data, and it's as simple as he didn't respect his own system about staying in compression, and the engineer that did the post-tensioning, I believe, didn't understand he should not post-tension number 11 and number 2 in the sequencing first. It changes the profile of the deck when you go to do the rest of the post-tensioning. So say you put 350 kips in here, but you've already preloaded this deck with these other strands. they should have focused on the deck and made sure the deck stayed rigid. Surveyed it multiple times to make sure it always stayed rigid no matter what. And then they should have load tested it. That's with water bladders, etc. in the staging area, not out in the real world. This was a one-off bridge. Don't do it in the real world out there. Do it in the staging area. Bladders, that's water. You know, set some concrete blocks up there if you like, but it should be equal distribution, similar to the human trafficking that would be up there. I kind of like the way I always say human trafficking. So there you are. There you are. Oh, so this system, I locked that in. I welded that section. I loosened the bolt, and just pretending like if I could just add load here and push it down, yeah, it would slide a bit. But I just can't do it because you can't slide the one individually down because it's still connected to the nodal area here, which means it was connected here. If this would be intent, it would have to make room, arch it to slide down. It would have to push this out of the way. For this to slide, this is still a nodal area locked in. It has to move, translate all of this. And it would also be implying that the canopy is the one that started the deck to the collapse because that's sliding. It was not. It was the deck deflection, not the canopy. Again, and it's multiple design mistakes. The diaphragm, how they ran the A and B through the diaphragm over here, how this diaphragm is different, how it wasn't in tension, all the compression all the time. The tension it's slacked up. The tension they put in it to keep it in compression all the time. I don't care about that redundancy thing because there's multiple. I mean, you don't have a redundancy battery in your system, do you? In your car, do you? Where's your redundant battery? You carry one? You have a redundant wheel on your wheelbarrow? You have a redundant wheel on your trash can? Come on, do you have a redundant driver's door? There is no redundant rail. You have a redundant railing sit on your railing to go down the house as you walk down your house. No, everything's got a critical fracture piece of the structure that will cause a total failure. You know, one cylinder failing in the car, one cylinder ring failing in the car can cause the whole car to fail. So this redundancy system is kind of ridiculous. I mean, this would have to be two different bridges, a truss system and then a post-tension system. Both of them were capable of operating individually from each other. Show me that redundant bridge. Now, I do know there's some. You've got your truss system on a lot of structures, bridges, and then you also have the cabling. But neither one can stand by itself. Now, there is a lot of the segmental bridges that are very interesting. Now, if you could add the segmental bridge and then put a cable stay bridge with the segmental bridge that you put together, that would be redundant. But their cost is prohibitive, and they won't do it. They only do they won't do it. They won't do things like that. All right, take care. Incidentally, they are building a bridge again there. Ending the video. A walkway under the water with flooding, taking care of flooding with pumps and all would work, but they want to make this a place to be, quotes. All right. Hopefully this was helpful to you, Dr. Ronald Ng, or anybody else watching it, and Professor Lehman, and anybody else who attempts to do this bridge structure evaluation. Think about everything I said. Go find it. I did videos on it, but now I've been shadow banned from that showing up in searches. I'll give you a playlist, but it's huge. There's 300-400 videos I have of this structure.